Our next speaker is Sarah Chasins, and this is, of course, I think as Vikas mentioned earlier about his students, actually, this is a personal pleasure of mine because you were one of my interns at one point actually working a deep learning system at Microsoft, and although you are not necessarily purely probabilistic programming, you do work on program synthesis for social sciences, and fortunately, they have to think about probability as well.
Okay, hi everybody, I'm Sarah. I'm going to be talking about some joint work that I did with Mangpo, who just recently graduated and is now at Google Brain, so that email is going to be out of date real soon. I'm going to be talking about how we can go from essentially a blank page to a full PPL program given very little input. And I'm going to start motivating this by basically putting in the same slide that a bunch of talks have had over the course of the couple days here, which is that writing a PPL model for the folks outside of this room is pretty hard. I basically think I could have stolen a slide like this from a bunch of different talks. The folks who are trying to reason about data, usually what they want, or at least from my experience is what they seem to want, is to grab that tabular data, like other folks have said, throw it into a system, get out some insights. They're not necessarily well equipped to reason about the patterns in their data, to reason about statistics, and to then sit down and formalize all of that in a programming language. But I think what is easier, what I'm going to assert is easier, is to then write PPL queries and even to edit an existing PPL model. And the reason I've been thinking about this is because I work with social scientists, and of course they have a bunch of data sets for which they would like to get some insights. And so maybe they want to ask some questions about, you know, I've run this experiment, I have this data, it represents something about the world, and I want to think about how likely certain events are. Or maybe I want to look at, there are some interventions that I could run. So I could go in and try to change this feature of the world. How would that affect the likelihood of something? Should I bother to pursue this intervention? Or they might even want to make a predictor or a classifier depending on what their goals are. So right now, if they wanted to do this with PPLs, they would have to sit down and think about the patterns in their data, and then they would have to think about statistics, which they may or may not understand well, and then they would have to sit down and use a programming language, which again, they may not be that good at programming, so most of the folks I work with have maybe written an R script or a Python script for data analysis, and it was kind of uncomfortable, and that's about the limit. And then they're going to also write the PPL query by just sort of sitting down and thinking about it. The goal for my work is, can we at least make them not have to write that PPL model? Can we get that from synthesis? And so the question from my work is basically, can we go from blank page to full-on PPL model with minimal user inputs? And it turns out that as long as you restrict yourself to a particular class of input data, the answer is yes. So from this point forward, we'll ignore writing the queries. We're happy to let the user continue writing those. But we want to drastically reduce the amount of sort of insight that the user needs to bring to getting the PPL model. All right, so the goals are a little wacky and weird compared to some of the other systems we've seen. Basically, we want to really emphasize that the inputs have to be minimal, so don't ask the user for too much. Fast synthesis is desirable. It's not the key for sure, but it's definitely helpful to have. Above everything, we really want readable outputs. So this needs to be something where they can sit down and read it and understand it and tweak it. Ideally, they could lift it right out of the program and basically publish it as the model of the data that they're studying. And also, ideally, we'd like them to really be able to explore various readability levels. So once they've got a program that expresses their data, can they basically explore different levels of readability and accuracy, sort of trade those off so that they can get to the level of readability that they want for their particular use case. Okay, so the problem statement, this is going to be sort of a PL view of the problem statement because this was originally a PL talk. Basically, we have a constraint on the space of acceptable models, a number of constraints. So here are various topologies. Of course, each of the topologies is going to correspond to a variety of concrete PPL models because, of course, we can have different distributions at the nodes and also different conditionals and different conditions within the conditionals. Different conditional probabilities for the various distributions. So the user is going to give us a causal order hypothesis. And basically, we're not going to ask them to say which variable is going to affect each other variable, but we are going to ask them to say, if there is a relationship between variable A and variable B, then you have to tell us which direction it would flow in. So if there is a relationship between burglary and alarm, does the burglary cause the alarm, or does the alarm cause the burglary? And then that will allow us to eliminate some of these topologies. We're also going to ask the user for a constraint on size, and that will allow us to eliminate some others. That's kind of fuzzy. That doesn't really reflect how it actually happens in the system. We actually give them some finer grained controls over the size of their output programs, and it basically happens after the main body of the synthesis process, but that's a good way of sort of thinking about the problem in general. Okay, so given some samples, like I said, we're taking a limited subclass of the types of input data you might be interested in. Our class is each column represents a random variable, each row represents basically a run of the program, a world. We take in also the user's hypothesis about the order of variables, and we take in a desired size k of the output model, and the goal is to get the best model that satisfies all of those constraints that maximizes the likelihood. We're going to be approximate, but that's the goal. Okay, so here's our tool. We have broken the synthesis process down into 3 stages. So first we do program structure generation, so basically that's going to pass a topology onto the stochastic synthesizer. Within the synthesizer, we're going to basically mutate the current program. We start with basically a sketch of the program, and then we go ahead and fill in the holes in the sketch with a data fitting process. We pass it to a scoring function that does likelihood estimation, and we go around that loop until we're happy with the program that comes out. Pass that on to program structure reduction, which is where the user gets to control how small, how readable that output program actually is. And so these are the inputs that we're basically seeing flowing through the system. We pass the topology into the synthesizer. It's coming up with a skeleton program. It's filling in the holes in the program. It's going ahead and scoring that. And eventually, we pass a concrete program out to the program structure reduction and a smaller concrete program out of the entire synthesizer. We'll go through these basically one by one. Okay, before we dive right in, the languages here, we have sort of a custom IR that we're using right up until CodeGen when we produce the final output. Nothing crazy, pretty much exactly what you would expect. The output, eventually, we do put it out in a subset of blog. We could do CodeGen to other languages. It's not super critical. Okay, so we put in the causal order hypothesis to the program structure generation, and the output is going to be our topology. What we actually do is just use the transitive closure. So if the user gave us this causal order hypothesis, then earthquake was first, so earthquake is going to have a direct connection to everything else. Burglary is going to have a direct connection to everything but earthquake, on and on and on. A couple notes on why we did this. So for those familiar with sketches, this is just sort of a general note about how to think about these topologies. For the purposes of this talk, it's pretty safe to think about the program sketch / program skeleton being essentially a model structure. It's a little fuzzy, but that's a good way to think about it. If you want to pop in a different way of learning the model structure, then this is the spot to do it. This is all factored out, so it's totally fine to actually put in some other way of generating the topologies. We can still do the exact same process in the later stages, no matter how you actually choose to generate the topology. And we actually did play around with a couple other ways of doing it. I'll tell you a little bit later why we ended up using the transitive closure approach. Okay, now into the synthesizer. We're getting that topology as our input, and we're using that to make our very first sketch of the output program that we want. Basically, inside we're running simulated annealing, and so at each stage we are generating a neighbor candidate program, and then we're going to go ahead and evaluate that. So to generate that candidate program, we basically randomly mutate the current program, tune it to the data, and then once we do that, we go ahead and score it, and we do this repeatedly. Okay, so what do these mutations look like? So here you can see a sample mutation where we have replaced this 15 threshold with the 16 threshold. Now, what gets a little weird here is, of course, all of the descendant in the AST are now no longer tuned to the correct data because, of course, we've changed which parts of the data set are being represented in the 2 branches. And so we go ahead and we pop out all of those old parameters, replace those with holes. Now, how are we going to fill those? This is where our data guidance actually comes in. So at this point, we basically, we navigate the AST. We grab the path condition for the particular distribution whose parameters we're trying to fill. We basically turn that into a filter on the database of the input data. Nothing too crazy there, exactly what you would expect. And then we can use that to actually tune the parameters. All right, so then we get our complete and concrete program, which we can then actually evaluate and score. For scoring, we do likelihood estimation. This is following the approach taken by a prior tool, psketch, using a mixture of Gaussians. We add support for a few new distributions, and you can see the CAV paper for that, but it's nothing too crazy. Once we have the output from the simulated annealing, we go ahead and pass it to the program structure reduction. And the idea there is that the user is going to tweak a couple parameters of our reduction algorithm to get the basically size of program that they want. And the idea is the algorithm is actually reasoning about how similar individual subtrees, individual branches are. and it's also reasoning about how much data was used to tune them. So in this case, we're trying to figure out, okay, does Mary calls actually depend on John calls? Is that really affecting Mary calls? And we might think, you know, if this has been tuned on lots and lots of data, 0.75 is pretty far from 1, so maybe that is actually different. But if we find out that one of those was tuned on just 2 rows of data, maybe we're not so sure. And so then we can go ahead and collapse that if we prefer. Obviously, this doesn't always make a huge difference if you have few variables in the first place. Maybe this isn't going to make a big difference. But even if you have a fair number of variables but few key connections, this can quickly make a very big difference in how readable your outputs are. So this is just sort of one small variable. This is already making a big difference. Okay, eval. We're going to go pretty quickly through this. We had some benchmarks. Each of them was a ground truth blog program. We had some rows of data for the training data. We had some rows of data for the test data. I talked before about how we're using the transitive closure. That's so that we could give the user maximal control over the size of the program at the end stage there. But we did want to make sure that we weren't totally giving up performance by doing this, so we did compare against a couple of other strategies. It's mostly safe to ignore those except to see that we really aren't losing out on too much performance with the transitive closure approach, which you see in pink. As you can see, the average synthesis time is less than 21 seconds, so we're pretty happy with that. The output programs are quite close to the ground truth likelihoods, so we're very pleased with that. We also really wanted to check and make sure that size reduction isn't hurting our likelihood too bad. And as you can see, it's pretty good. So this is where we're just altering one of the parameters of our reduction algorithm. And you can see that in some cases we're growing from like 130 for healthiness over there all the way down to programs of less than size 20. Size here is just the number of individual distributions that we have at the leaf nodes of the AST. And you can see we're really not sacrificing likelihood as we do those collapses, so we're pretty pleased with that. We also wanted to check, since the idea is to basically give this to social scientists and let them pour in real data, can this handle real data? We used a US Department of Transportation flight delay data set, pretty big, well, medium big, basically because it's something that's already been analyzed in the past and folks have drawn a lot of conclusions about the patterns that are in it. And we were able to refine some of those patterns. So like, it turns out as it gets later in the day, there are more delays. Good knowledge for everyone going to the airport after this. And we were able to recover those exact same patterns. And when I say recover those patterns, I mean we literally opened up the program that came out and looked at it and said, oh, look, that's the pattern. You can tell that this is a slide for a PL conference because we're bragging about how cool PPLs are and trying to get them to like buy into, hey, you probably want to have a PPL because you can do all these cool things like a delay predictor. So we did a predictor, and you can see we got a pretty reasonable error, less than about 15 minutes. We compared against the baseline. We were better than baseline. I want to wrap up real quick with some thoughts about why we care about minimal inputs and why we care about readability. So the background here is that I'm interested in program synthesis for social scientists, and I was hoping that this tool would ultimately end up serving basically that same audience. And so the idea was always to put a synthesizer like this into a tool, something like what you see over here. Never actually built this UI, but you know, the basic idea is user uploads a data set, they put in their causal hypothesis, we see the score changing, we see, you know, the synthesized program, the current program flashing by. Eventually they say, okay, stop there. They mess around with the parameters for our reduction algorithm over there on those sliders up at the top, and eventually what they get out is a program that they like, and then they can do some edits, they can test their interventions, whatever it is they're trying to do. Now, I'm looking forward to the job market, and looking at that, I realized that I had to stop working on this and focus on my thesis work, but I still think that this is a really, really valuable direction. And I would love to see some folks looking at not just tools like this, but also other synthesizers that focus on asking for very little from the user and producing outputs that the user can really read and use to get insights. I think this could be really, really beneficial for getting PPLs out to a broader and more diverse audience, and ultimately putting these extremely powerful programming abstractions in the hands of basically non-traditional programmers. I definitely hope to get back to this work myself, but I would also love to see other folks, maybe some folks in this room, getting into this general line of work. I think that would be really exciting and potentially really high impact. One last way of looking at what this work did, I think this might be interesting to some folks in this room as a way to think about what this work is doing relative to other work. So basically, where a standard search and score, if they're trying to handle revalued variables, would first fix basically how they've discretized the variables, and then go ahead and iterate on the model structure, the topology. This work is doing, and when I say that they would fix the discretization, because they're doing that up front, that means that they are basically putting everything into teeny tiny little bins, bunches of little teeny tiny little bins. So then once they actually go from that to the program that they dump out, it's going to be this massive set of huge switch statements, and it's going to be totally overwhelming and not readable, which of course is totally fine because that's not something they were going for. But since this work is focused on readability, we actually sort of flipped this. So first we fixed that topology. Then we went ahead and actually iterated on what should be the discretization, what should be the conditionals. And then after that, the user can go in and make a certain subclass of allowable edits to the topology. But really, it's mostly about fix the topology, iterate on the discretization, sort of this flipped order, which I think is an interesting way of looking at it, maybe to some folks in this room. And with that, I would love to take any questions.
It looks like the structure of the programs you're synthesizing doesn't ever have loops.
That's true.
Don't you think, or could your method also synthesize loops? And would you say that sometimes the programs get more readable if they have a loop instead of a bunch of nested if-then-else statements?
So I'm trying to think if I've run into any cases where it would get more readable with a loop. I don't think I've run into that yet. But I could certainly imagine it happening, and I would love to extend to that.
Flow is not an imperative language. It doesn't have loops. Or recursion, you just have a logical variable and it's quantified. But recursion, sure.
So this isn't restricted to Blog, although of course we are using Blog as the output language now. But yeah, that's also a good point.
Just as a ballpark, what is the number of columns that this scales to? Right, so if you're a social scientist and you have lots of variables, at what point do you maybe hit the limits of what's computationally feasible?
So,
Could you repeat, actually?
oh, sorry. So the question was, how many columns can we scale to, especially considering that social scientists might often have data sets that are going to be quite large in that dimension? I think the largest we tested was something like 30 columns, which is not huge. It's okay.
Yeah.
I would definitely like to scale to more.
I think that's pretty good.
Just following up on the question about columns, so for social science data sets, have you thought of techniques where, especially with large number of columns, to learn the causal hypothesis, the causal ordering, using structural learning algorithms or even classical algorithms from Collar and Friedman, or lines along that work? Because you can imagine in practice, the causal ordering can be hard to specify. Or what are your thoughts on that?
I actually have a bunch of mixed feelings on this question. So definitely I have thought about this because that's one of the first things you think about is how can I eliminate even more of the information that the user is having to provide right now. It would get a little weird if we're suddenly reversing the order that is intuitive to them. If suddenly alarms are causing burglaries, I think they're going to be freaked out and not enjoy that. But that said, I do think it was a really important design choice to factor out all of the program structure generation parts of this work so that you could sub in any particular. So the causal order hypothesis, we basically throw that away after we've done that program structure generation step, that first step there. And that's all factored out, and you can plug in whatever you want there. So I do think it's possible to play around with these and see if that's a good approach for future.
All right, let's thank the speaker.